respected judges, professors, and my fellow researchers. Let me begin with a simple question. What happens to a tire after it finishes its large journey on the road? Most of us assume it gets recycled. But that's not the reality. Every year, over 1 million waste tires gets discarded worldwide. Problem is not just the number. These tires do not decompose easily. They occupy our landfills for decades, create fire hazards, and even become breeding grounds for mosquitoes. But what if I say the same tires can become the part of the buildings and infrastructure that we all construct? Not a waste, not a pollution, but a construction material. Today, I, Paritosh Kadam, on behalf of my team members, is humbled to present my research title, Experimental Study of Rubberized M20 Concrete using Cubical and Angular Tire Aggregates. To understand how global waste problem can be converted into a sustainable construction solution, I will structurally explain you and walk you through 5 key sections. First being the introduction, explaining background and problem statement, then the research objectives, experimental methodology, results and analysis, following application, last but not least, conclusion. So, what is the need and importance of integrating waste tire aggregates into concrete? So, the thing that motivated me is that rubber has been contributing significantly to industrial development since its extraction from Hevea brasiliensis from 18th century in South America. Natural and synthetic rubbers have been an essential part in automobile and construction industry. As I've already said, that these waste tires have been illegally landfilled, stockpiled and dumped, leading to fire hazards. To mitigate this issue, waste tire is utilized in civil engineering application called rubberized concrete, where rubber partially replaces composite aggregates to improve impact resistance, ductility, vibration damping, and thermal and acoustic insulation, and most importantly, environmental sustainability. But the research gap that we all found was the influence of rubber aggregate shape on concrete compressive strength performance have not been evaluated yet. Our research fills this gap by evaluating the mechanical performance of rubberized concrete by comparing compressive strength with standard M20 concrete. The research objectives are to investigate effective utilization of waste tire rubber, compare the compressive strength of standard M20 concrete, rubberized concrete with cubical rubber aggregates, and second, angular rubber aggregates, and evaluate the influence of aggregate shape on bonding characteristics and strength development. Then, to analyze strength performance at 7 days and 28 days. Then, assess the feasibility of rubberized concrete as sustainable construction material. And finally, to identify potential applications of rubberized concrete in non-structural and structural elements based on our experimental results. So, following is the experimental methodology applied by us. Materials used were Portland pozzolana cement conforming to IS 455/1989. Fine aggregates used are natural river sand. Coarse aggregates used were crushed stone. Rubber aggregates that, as said, were replaced by scrap tire rubber. Two shapes we considered. One is cubical shape, second is angular shape. And the admixture we used is associate FRX, Fine Plus, and portable border. The mixed design is as follows: grade of concrete N20, rubber replacement 6% of coarse aggregates, and totals of 18 cube specimens were casted by us. 6 of standard M20 concrete, 6 of cubical rubber concrete cubes, 6 of angular rubber concrete cubes. Cube sizes standard 150 by 150 by 150 mm. Volume standard 0.003375 m3, and curing period 7 and 28 days. The experimental methodology covered mixing, casting and testing. So let's begin with mixing process. Mixing process, materials were weighed as per mixed design as I shown in the earlier slide. Dry mixing of cement and aggregates in drum mixture, addition of water and admixture. Then mixing continued until uniform consistency was achieved. Then slump test was conducted to check the workability. Then we casted concrete was poured into cube molds of standard dimensions. Then proper tamping was carried out. Surface was finished and labeled. Specimens were demolded after 24 hours. and then they were, after air curing, they were water cured until testing age of 7 and 20 days. So how did we carry out the testing procedure? We conducted using CTM, compressive testing machine, and then load was applied until failure. Strength was calculated in MPa. An objective of all this experimental methodology was simple and clear. Compressive strength of standard M20 concrete, rubberized concrete with cubical rubber, rubberized concrete with angular rubber. And following is the comparison shown in result and analysis slide. So, talking about 7-day compressive strength results. So what it is showing that in standard M20 concrete we have achieved 14.18 MPa, but this is how the shape influences the strength. Rubberized concrete, cubical rubber of 20 mm size, it shows 12.56. It is showing reduction compared to standard M20 concrete. Whereas angular rubber 12 mm size is showing at early stages of curing only it is showing 14.75 MPa. And talking about 28-day compressive strength result, standard M20 concrete is showing 24.80 MPa, whereas cubical rubber is again showing less, 22.25. Whereas angular rubber is showing more compared to 24.80, it is showing 26.55, which is a very important point. So, what we can interpret and what are the observations? Angular rubber aggregate concrete achieved highest 28-day strength. Cubical rubber aggregate concrete exhibited reduction. So, these results indicate that aggregate shape significantly influences compressive strength performance in rubberized concrete. So, the results and analysis, we can consider that for standard M20 concrete, design target strength is 20 MPa, 28-day strength is 24.80, which is normal strength development. Rubberized concrete, 6% replacement. We are considering 6% replacement of cubical and angular. But for cubical, it is showing reduction 22.25, whereas for angular it is showing 26.55. Reduction is 11.4% lower and 10.3% lower respectively at 7 and 28 days for cubical. Whereas it is 4% higher in 7 days and 4% higher at 7 days and 7% higher at 28 days for angular. So, result and we can why the cubical is showing strength reduction due to poor adhesion, stress concentration at rubber cement interface and reduced stiffness. This trend clearly demonstrates the significant influence of aggregate shape on concrete strength performance. So, what we can conclude that based on experimental investigation, it is concluded that compressive strength of rubberized M20 concrete is significantly influenced, and incorporating concrete angular rubber aggregates exhibited higher compressive strength compared to both standard M20 concrete and concrete with rubber aggregates. Applications, as I said, is structural or semi-structural, non-structural, pavement and infrastructure and functional application. I have considered 4 different verticals in which this concrete with various tire aggregates can be utilized in both non-structural, structural, pavement, infrastructure and functional application as follows. Because as I said in first slide, it also uses acoustic and damping insulation. So references were as follows. Thank you for your attention, and I will welcome. I'm happy to welcome any questions. My closing remarks would be that the tires that are being utilized in vehicles right now will help build the roads of future. By converting waste into construction material, we are moving one step closer to sustainable infrastructure. Thank you.